he assigned values to each of the elements, atoms of each of the elements in the periodic table. Okay, and fluorine being the most electronegative elements has a value of 4.0. Hydrogen 2.2, 2.1, somewhere in that neighborhood. So each atom has a different electronegativity value. But how do we define electronegativity? Ability of an atom to, in a molecule, to attract electrons toward itself. If you have the same ability, two hydrogen atoms, each one has the same ability to attract electrons towards itself, then we say you have an equal sharing. The electron pair will stay right in between, in the middle, right in between the two hydrogen atoms. But if you have hydrogen and oxygen, well, they have different ability to attract electrons towards oneself, towards itself there. As a result, the electron pair between hydrogen and oxygen atom is leaning more towards oxygen, because oxygen is on the far right side of the periodic table, more electronegative. Okay, so know this definition. We mentioned this definition in chapter 8 already, and officially in this chapter we introduce electronegativity. Okay, and again, definition is part of learning chemistry there, and I do expect you to memorize all of these important definitions. Now, Linus Pauling, a very famous chemist there, and he won Nobel Prize twice, and once for his contribution in chemistry in the 60s, and the other time, the second time when he won Nobel Prize, and was Nobel Peace Prize. And he was the pioneer of trying to get the whole world realized what we got ourselves into during the Cold War. And you see the Soviet Union and the United States were building nuclear arsenals there, and we have enough nuclear arsenals to destroy this planet. So we said, well, we should stop building them. We should ban nuclear testing. And so he pioneered all that work, and he won a Nobel Prize for peace. So, two-time Nobel Prize laureate, and Linus Pauling, not only a chemist but also a peace lover. And he has a lot of advices for people. And he said, well, taking a large amount of vitamin C actually is beneficial to your health, and you should take his word for it. Say 1901, 1994, 93 years old. So he takes a lot of vitamin C throughout his life, and that's the advice he gave you. Okay. So talking about electronegativity, this is something in your textbook there. We're looking at the random, well, arbitrary values assigned to each of the atoms there, and based on how they interact with one another, and the same kind or different kind of atoms there. So hydrogen is 2.1, lithium is 1.0. As you can see, electronegativity goes down from top to bottom within the group, and goes up from left to right within the same period. So in general, this is the trend. Going from the lower left corner of the periodic table to the upper right corner of the periodic table, the electronegativity is increasing. So whoever is on the far right side of the periodic table, they are said to be more electronegative. They have a stronger or higher electronegativity. And the elements on the left side of the periodic table, metals, they have lower or not as strong as electronegativity. It only makes sense. Electronegativity, by definition, is the ability to attract electrons towards itself. Metals don't like electrons. They tend to give electrons out, so they have low electronegativity. Non-metals have high electronegativity, while they try to attract electrons toward themselves. Okay, so this is the, when we're talking about the periodic trends yesterday in chapter 8, we give you this diagram here, and this is something that we do want you to remember. The general trend in terms of the electronegativity. Now, how do we use electronegativity to judge whether a particular chemical bond is polar or nonpolar? Well, we look at the chemical bond, the situation of the electron sharing within the chemical bond. Now, if you have a chemical bond, and you can actually detect one end of the chemical bond is more negative than the other, so in that case, we say there is an obvious separation of charge, then we have what we call a polar bond. But if you look at a chemical bond, there is no obvious separation of charges there, then that's a nonpolar bond. So this is very qualitative. Can we quantify how much difference is enough difference to qualify them as a polar bond? how much difference is not enough difference to qualify them as non-polar bound. Yeah, using the electronegativities, we can quantify, we can actually calculate the difference between the two atoms, okay, and in terms of electronegatividity. And if the difference falls within a particular range, and the value, the difference between the electronegativity value there, then if they falls in between a particular range, we say, well, this is polar, this is non-polar. Okay, so what are the ranges there? Well, we can take a look at some non-polar molecules first. Now, for non-polar bound, in non-polar diatomic molecule, hydrogen gas, fluorine gas, that would be a perfect example. Now, if you have two hydrogen atoms connect with one another, each has the same ability to give or take electrons from one another. So the electrons are being equally shared by those two hydrogen atoms there. Okay, the fluorine and fluorine, fluorine is the most electronegative element, but each one has the same ability. When you put the two together, they have the same ability to take electrons from one another, so they are equally shared. Okay, so these are the examples of non-polar bound. What happens if you put hydrogen and fluorine together? Well, hydrogen and fluorine, you look at the difference between the hydrogen and fluorine in terms of electronegativity. Hydrogen 2.1, fluorine 4.0. The difference is 1.9. Okay, so that's a fairly large difference there. So in this case, we would say fluorine has a much stronger ability to take electrons toward themselves. So much higher electronegativity. Okay. Hydrogen compared to fluorine is not as electronegative. As a result, this pair of electrons is going to be closer to fluorine, further away from hydrogen. So in this case, we end up with what we call a polar bound. Okay? So using hydrogen iodine as another example, hydrogen would be the atom that bears partial positive charge. Delta, the Greek letter delta, represent the charges there. Put a positive sign in there, that's a partial positive charge. Iodine will bear a partial negative charge. Now, if you look at the location of these two atoms in the periodic table, hydrogen group 1A, iodine group 7A. One is on the left, the other is on the far right. So anything that's on the right side of the periodic table would be more electronegative. As a result, they are going to bear more negative charge. Because when these two types of atoms connected with one another through a chemical bound, we say we end up with a polar bound, meaning there's an obvious separation of charge. One side is more negative than the other side, or one side is more positive than the other side. Okay, so that's the separation of charges there. Now, covalent bonding, we say electrons are being shared. When you have non-polar bound, electrons are shared equally. In the example of hydrogen gas, fluorine gas, whenever you have the same type of elements connect with one another and form the chemical bound, the chemical bound is nonpolar because each one has the same ability to give or take electrons from one another. Okay? As a result, we have an equal sharing. As a result, we have nonpolar bound. And then for the polar bound, electrons are not shared equally. Now remember the other extreme. Ionic compound, electrons are being taken away from one, and then the other elements will actually take the electrons from the metal elements, and the non-metal elements will take the electrons away. So there's a transfer of electron. In this case, it's not a transfer yet. We're not getting there yet, but the electrons are being shared unequally. Okay, so there's an unequal sharing, and a little bit more unequal sharing will probably, when you go further